basically what we just went through gives us this posterior probability of a specific path given a specific set of observations. Why? Because we can use it to compute both this numerator for a specific path, and we can use it to compute this probability summation in the denominator summed over all possible paths. We'll get into the computational complexity of this a little bit later. Said the summations are not fully coupled because they factor in this way. So now we can zero in and start to get, for a specific theta t, we can get it from the exact same thing at theta t minus 1, summed over all possible values of theta t minus 1. And in this way, we can compute in the forward direction all of the probability path summations that we need. Okay? It's called forward because we start at t equals 1 and we end at t equals n. Okay? So a couple of principles are at work here, just as they were in Viterbi. One is that we're basically using a recursive definition that, from this we can get this. So all we have to do is be able to get this at the beginning theta 1 x1, and we're good for the entire sequence. And then obviously we're using summation to eliminate the nuisance variable, and in that sense sum efficiently over all possible paths. Okay, so we've basically already solved this. And now we get to the second problem of wanting to get the posterior probability for a specific variable theta t given the complete observation sequence. So now we can ask the question, were they cheating on this particular roll? Okay, which is a different question than saying, well, I think this is the whole history of when they were cheating versus when they were playing fair. Sometimes this is a more useful question to ask. Okay, so what we can